Welcome to Spring LIB.
We are given an overall cell reaction, and we first want to find the values of both the standard cell potential as well as the standard change in Gibbs free energy of the overall reaction. Based on the overall reaction, we can break it down into these two half reactions from the standard reduction potentials table, along with the corresponding half reactions. If we multiply the top equation by 2, then we see that we can cancel out 4 moles of electrons on either side, as well as 4 H plus ions on each side. And so now we can clearly see that we have 2 H2O liquid going to O2 gas plus 2 H2 gas. And again, that is the overall reaction that we are given in the problem statement. And now we can find the standard cell potential based on those two reduction potentials that we were given in the table, and we flipped the sign of the second half reaction so that it undergoes oxidation to fulfill the form of the overall reaction that we were given. And when we add those two potentials together, we see that it comes out to negative 1.23 volts. And now we want to find the change in Gibbs free energy at standard conditions, which is equal to negative NFE. N is equal to those 4 moles of electrons that we canceled out. F is Faraday's constant, which is 96,485 coulombs per mole of electrons. And the standard cell potential we just found was negative 1.23 joules per coulomb. And so when we calculate that all out to find delta G, we can divide by 1,000 to get the final answer in units of kilojoules. And when we do that, we see that it comes out to about 475 kilojoules. And now we want to use thermodynamic data in the appendix in order to solve for these same two values at temperatures of 0 degrees Celsius as well as 90 degrees Celsius. And we are assuming that delta H and delta S are independent of temperature. So we know that the overall equation that relates delta G to those other two variables is delta G equals delta H minus T delta S. And we know how we can find the overall change in enthalpy and entropy for a given reaction based on the data in the appendix. And so once we have those values, we can plug in a temperature of both 0 and 90 degrees Celsius to determine delta G, and then we can back solve using the delta G equals negative NFE equation to find the standard cell potential at each temperature. So we first need to find delta H and delta S at standard conditions for that overall reaction, because they're independent of temperature and will be equal to the same values at either one of those temperatures. So starting with delta H, the change in enthalpy of the overall reaction, we know this is equal to the total change in enthalpy of the products minus the total change in enthalpy of the reactants. When we look at the product side, we see that we have O2 and H2 gas. Those are both naturally forming diatomic gas molecules, and so their enthalpy of formation is 0 in either case. So that means that the total enthalpy change of the products is equal to 0. And then we subtract the total enthalpy change of the reactants. We see we have 2 moles of liquid water. So we multiply those 2 moles of H2O liquid times the value for the delta H of formation at standard conditions for liquid water, which is from the appendix negative 286 kilojoules per mole. We cancel off units of moles, and we are left with total energy units for the change in enthalpy of the overall reaction. When we cancel out those negative signs, we see that that comes out to 572 kilojoules. And now for delta S, we again do the total entropy of the products minus the total entropy of the reactants. So for the products, we have 1 mole of O2 gas and 2 moles of H2 gas. So 1 mole of O2 gas has an entropy, a standard entropy value of 205 joules per mole times Kelvin. Then we add this to the other product where we have 2 moles of H2 gas, and its standard molar entropy is equal to 131 joules per mole times Kelvin. So that's for the products, and then we subtract for the reactants. Again, that's 2 moles of liquid water. So 2 moles of H2O times the standard molar entropy for liquid water, which is 70 joules per mole times Kelvin. And so when we calculate that all out, it comes out to 327 joules per Kelvin. So now, at a temperature of 0 degrees Celsius, we can solve for delta G and the cell potential. So delta G at standard conditions is equal to delta H at standard conditions, which we found was 572 kilojoules, minus T, which 0 degrees Celsius corresponds to 273 Kelvin, times delta S at standard conditions, which we calculated to be 327 joules per Kelvin, but we need to divide by 1,000 to convert to kilojoules, so that after we cancel off units of Kelvin, we can subtract the units of kilojoules. And so that comes out to a value for the change in Gibbs free energy at standard conditions at 0 degrees Celsius to be about 483 kilojoules. And now we know that delta G equals negative NFE, and so the standard cell potential is equal to delta G at standard conditions divided by negative NF. And we saw that was 483 kilojoules. We need to convert this into joules, so we get the cell potential in units of joules per coulomb, or volts. So we multiply by 1,000. So we have joules divided by negative N, which again was 4 moles of electrons, times Faraday's constant, 96,485 coulombs per mole of electrons. And so that cell potential at standard conditions at 0 degrees Celsius comes out to about negative 1.25 volts. We compare and see that that is close to the actual value, negative 1.23 volts. And now we do the same for a temperature of 90 degrees Celsius. We use the same values for delta H and delta S that we calculated, since they are independent of temperature by assumption. So delta G at standard conditions is equal to delta H which again we found was 572 kilojoules, minus T, the temperature 90 degrees Celsius, this time corresponds to 363 Kelvin. And then delta S, when we convert to kilojoules again, is 327 times 10 to the negative third kilojoules per Kelvin. And so when we calculate that out, the change in Gibbs free energy at standard conditions at 90 degrees Celsius is equal to about 453 kilojoules. And now the standard cell potential is equal to the standard change in Gibbs free energy divided by negative NF, which is equal to 453 times 10 to the third joules divided by negative 4 moles of electrons times 96,485 coulombs per moles of electrons. So we're left with units of joules per coulomb or volts. And the standard cell potential at 90 degrees Celsius comes out to about negative 1.17 volts.